Welcome to this YouTube channel. Today I'll be showing you how you can carry out molecular docking of drug polymer conjugates, and we'll be using ChemDraw, PyRx and Discovery Studio. Now the first thing to understand is what drug polymer conjugates refer to. Now drug polymer conjugates is a drug delivery system that consists of a drug covalently linked to a water-soluble polymer. Now you might be asking, why drug polymer conjugates? The presence of this water-soluble polymer causes an increased solubility in the system. Now this makes the drug to be more soluble and more bioavailable, especially at the target site. Now this is considering that most drugs are not soluble in aqueous environments. Now, secondly, the presence of the polymer also causes an increased stability of the system. A lot of drugs will degrade once they get into the body of living organisms, and that's even before they get to the target site. So the presence of the polymer causes them to be more stable till they get to the target site. Thirdly, the presence of the polymer can lead to decreased toxicity. Now, this is because the drug polymer system is expected to be stable until it gets to the target site, and that means that the drug will not affect healthy tissues. So it's likely that you find out that drug polymer conjugates have decreased toxicity when compared to just the drug alone. Now, it's important that you understand that this system is very useful, especially if you want to target a specific, if you have a specific target when you're working with your drugs. Now, we have a representation in figure 1 of our drug polymer conjugate, and you can see the water soluble backbone, you can see the drug, and then you can also see a targeting moiety that actually helps you to target a particular specific receptor. Now, why are we docking drug polymer conjugate? So that we can see if there's um, a better interaction between the drug polymer conjugate and the target receptor when compared to the drug alone. So you'll find out a lot of works on drug polymer conjugates will include molecular docking. Now, the first thing in carrying out molecular docking of drug polymer conjugates is that you model that conjugate. So you can use ChemDraw, you can use Avogadro, you can use several softwares to do that. And today we'll be using ChemDraw and Chem3D. Now, also, after you've done that, you have to optimize the geometry of the conjugate. Now, it's not just enough modeling your conjugate. You have to optimize geometry to obtain a structure that's representative of that conjugate in real life or under experimental conditions. Now, once you've done that, you prepare your protein, you carry out molecular docking, and then you analyze and visualize your results. So we are going to be doing that. Now, let's go to the practical session. Now, today we are going to be considering the antidiabetic potential of polyallyl amine hydrochloride vanillin conjugate. Now, Mahadik et al. In 2024 reported the synthesis of a particular um, drug. So today we'll be carrying out So today we'll be assessing the antidiabetic potential of a polyalenamine hydrochloride vanillin conjugate. And then we'll be working with the conjugate that was synthesized and reported by Mahadik et al. In 2024. You can see it. Now this is the structure of that conjugate. It was obtained by reacting vanillin with um, a compound that eventually produces that polymer. So today we'll be considering the So today we'll be assessing the antidiabetic potential of polyalanine hydrochloride vanillin conjugate. Now this conjugate was synthesized by Mahadik et al. In 2024 and was reported. Now you can see that this is the backbone. So today we'll be assessing the antidiabetic potential of a polyalanine hydrochloride vanillin conjugate. Now vanillin is the drug while the polymer is obtained from polyamine hydrochloride. Now you can see that this is the conjugate. You can see it. This is your vanillin, and then this is the polymer path, that system. Now, this conjugate system was reported by Mahadik et al. In 2024, and this is the target protein we'll be working with. Look at the code PDB1IR3. So I've shown us how we can select um, target proteins in earlier videos, and then if you have an issue selecting the correct. So today we'll be assessing the antidiabetic potential of polyamine. hy- So today we'll be assessing the antidiabetic potential of the polyamine hydrochloride vanillin conjugate. And this conjugate was reported by Mahadik et al. In 2024. Now, for this work, we'll be using this protein target PDB1IR3. In earlier videos, I've shown you what you need to do to select a target receptor. So I've shown you how to do that. Now, if you're having challenges doing it, you can just go through my channel and then you'll see a video that addresses it. Now, so the first thing to do will be to model this conjugate system. Now, look at this conjugate system. You have vanillin, which is the drug. You can see that this vanillin, this is coming from vanillin. So this is the drug, and then you have your polymer backbone. So this is the polymer backbone. So the first thing you have to do is to model this system. Now we've modeled the system, and then you can see. So this is our drug vanillin coming from vanillin, and then this is our polymer. Now looking at this, you observe that this is n. Now, in this case, we're using n equals to 5. That's why we have this. Now, depending on the system you are working with, if you have n equals to 10, then you should model it that way, maybe n equals to 20. But if your compound is very large, I mean, if your polymer is so large, then you may just have to use a representative fragment of that system to carry out molecular docking. Now, so this is structure we're working with. So first of all, what we need to do is to model this system, and then we'll be doing that using ChemDraw. So open ChemDraw. You should have ChemDraw installed on your system. So I would have ChemDraw. Now, so we have ChemDraw here. Okay, so this is good. So the first thing I will do is to model this um or draw this structure. So simply this is your benzene ring, and then you have um this, so this, this, and then have nitrogen, this, this, you have this, and then so we have one. So you should know how to use ChemDraw, and then I have a video on that too. So let's see how many. Um, one, two, three, four, five. Okay, one, two, three. Okay, so one, two. Okay, now the next thing we need to do. So it's an amine end. So NH2, 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 NH2. Now and then to make this a double bond. So this is double bond, cool. And then we have a hydroxy group, position 4. Sorry. Then position 3. We have a methoxy group. Okay. So I think we're almost there. Let me look at my structure. Oh, we have something else. One, two, three, four, five. And this is like, okay, this is it. Okay, I guess that's that. So now select it and then you try to clean your structure. So go to molecule and then go to clean up structure. Oh, so this is good. Now this matches what we have. Let's see it. See it. Okay, this matches what we have. So this is your conjugate. Now once you've drawn it in ChemDraw, the next thing is to transfer it to Chem 3D. So you can save it. Let's save it. Can save it as okay. I want to save this under downloads and then okay, good. So save it as vanillin conjugate. So what we need to do is transfer it to Chem 3D, and that's where we convert the structure into a 3D structure. We're going to be using Chem 3D. So sorry. So this is Chem 3D. So click on it. Now you should have this installed on your system. So what I will do is I will copy my structure. So and then I'll copy it and then paste it there. Okay, so this is Chem. Okay, so this is Chem 3D. So what I will just do is to paste it here. So now you can see that. Now, so you've modeled your, you've drawn your structure in a 2D form, and then you've pasted it here to convert it to a 3D form. The next thing you have to do is to optimize this structure. So click on, we're going to be using molecular mechanics to do that. So now sometimes it takes a while depending on the size of your compound. Now, while this is on, we are going to be using PyRx. So I would like to open PyRx just to keep it open. Okay, so now it's still yet to complete. Now, while it's still optimizing, let's try to prepare our protein. So we'll be using Discovery Studio. So open Discovery Studio. Now we'll be using Discovery Studio to prepare our protein. Okay, so PyRx is open. So we are not using it yet, but I just wanted it to be open. So now Discovery Studio is here. And remember, we'll be using Discovery Studio to prepare our protein. Okay, so this is good. So how do we prepare the protein we are working with? I showed you the protein, so I will navigate to um, first of all open molecule window. Good, and then I will navigate to the file that contains the target protein we'll be working with. So no. So what we'll do is it's under downloads. Okay, you can see it. Okay, good. Okay, you can see now this is the target protein we are working with. So I'll open it now, so you can see this. You can see this. Good. Now the next thing is to look for the crystallized ligand, because that will also give us information on the binding site we'll be using. So I think it's ANP. Good. So this is the crystallized ligand we'll be using. Mg301 and Mg302 actually are magnesium ion. So we're using AMP 300. You can go to the RCSB page and check, and you see that this is the most appropriate ligand you should use. So I will go here, click on the attributes. Now, once you click on the attribute, it will give you information on the dimensions of the docking site. So just select it, Control C. I like to copy it, and then you can open a notepad to save it. So open notepad. Okay, so I'll put it here. Now, so I'll call this X, I'll call this Y, and then I'll call this Z. Okay, so this is good, and then I'll save. Okay, so I'm not saving it here. I want it here. So this is one IR 3 dimension. So once I've done that, I can close it. So the next thing I would want to do would be to remove the co-crystallized ligand and then the ions that we have there. So I'll cut this, cut. I also want to remove this. Now the next thing I also remove is water. So this is good. So water is out. Now the next thing I want to do is to save this. So save as. So I'll save it as a PDB file. Save it as a PDB file. So but I will change the name so it to be one IR R3 without ligand. So I'll save this. So this is good. Okay. Now, so once you've saved this, the next thing you want to do is to go to PyRx. So we've opened PyRx. Now, to carry out the molecular docking of this system, it's advisable that you dock also using a standard. So I'll be using a standard drug. I'll be using Acarbose. Then I would also be using vanillin because I want to compare vanillin to that with its conjugate system. So I will also use vanillin. So I would like to draw vanillin here too. So let's go here and then so I will draw the structure of vanillin. Now instead of doing that, I will just convert name to structure and then simply vanillin. Okay, so this is it. So I can simply copy this and then paste here. Okay, so wow, this has completed. So we are done optimizing this structure. So what I can do is to save this. So I'm going to be saving it as a mol2 file. Don't forget, you save this as a mol2 file. You save it as a mol2 file. So I'll be saving it as a mol2 file. So come here. So this is mol2. Yes, that's it. So remember that it's a vanillin conjugate system. So you can save it. Good. So I'll save that. Now I also want to um convert the 2D structure for vanillin to a 3D structure. So I'll paste it here. You can see it. Now I will also minimize it. Okay, so complete. Then I can also save it. You can choose to just save or click on save as, and then we are saving it as a mol2 file. So this is vanillin. Good. Oh, this is good. So what I've been able to do is that I've been able to model the conjugate system. I've also been able to model vanillin, and then I'll be carrying out the molecular docking for this compound. So what do I do? Open PyRx, go to File, and go to Load Molecule. So I'll navigate to the directory. Okay, so I'll be using this without ligand, so I will import it. Okay, I'll also be importing the conjugate system and vanillin. So let's import this first, and then I'll be importing vanillin. So you can see that. And I think I have acarbose here. Okay, I think I have acarbose. So if I have acarbose here, I think okay, I have acarbose here, so that's fine. Now, so I've imported this. This is my target protein. So what you do is right click and then you simply click on make macromolecule. So okay, now the next thing for this, click on make ligand for this. So this will be a ligand. And then this also you make as a ligand, and then you will be using Autodoc Vina, so we want to run Vina. So it's telling us to select a ligand. So let's click, let's start here. So we start, and then let's select the ligands we want to work with. So let me look for them here. So vanillin. So what you do is you can hold control and then select it. So we've selected vanillin conjugate and vanillin. Now I would also like to use acarbose, which is a standard drug for anti-diabetic studies. Now if you bring your cursor where you find my cursor, you see that you have that it has selected the macromolecule as 1IR3, so we are good to go. So once you've selected acarbose, your conjugate system, and then the drug, remember acarbose and vanillin are there for comparison. The next thing we do is to um, click on forward. Now, also, it's wise that you also try to use the co-crystallized ligand. So, the co-crystallized ligand, you would have found it, I think that's ANP. So, it's wise that you also use that for docking so that you can compare. Now, so once we've done this, the next thing is to try to get the correct coordinates, and this is where some of us have challenges, but if you are very careful, you will get it. So let's open our dimensions. I think it was a notepad. Okay, so let me click on notepad. I think okay, so let me navigate. Okay, so we have it here. Okay, so you can see the dimensions you will be working with. So this is minus 23.766. So let me show you. Now this is your um, x-axis, this is your y, and this is your z behind. So for x, it is minus 23.76. So let's do that. Now you should be able to do that. Okay, fine. So we've gotten x. The same thing you should get for y, and also you should get the correct dimension for z. You may not get the exact same, but something that should be very close. Now we've been able to get the correct coordinates. So you can see that 23.76, 29.15, and 6.97. Now if you look at the coordinate, they're not exactly the same, but they're quite close, and that's what you should try to do. Make sure it's quite close to the coordinate you have here. And once you've done that, also make sure that the dimensions are not too far from each other. Once you've done that, the next thing is to click on forward. And then you can see that your molecular docking has started. Okay, so you can see it. So the molecular docking process has started, and then when it's completed, we'll analyze the results. Now, so the docking is complete. So what we can do is to um, see the results we have. Now you will see that there are results for different pulses. So this is for Acabos. The best result was minus 8.4. Let's, okay, for the conjugate system, minus 6.9. And then for vanillin, vanillin is minus 5.1. There's a way to see it clearly. So simply come here. So once you click on target, to arrange it according to target. So we have vanillin for that target minus 5.1, the conjugate system minus 6.9. So you can see that the conjugate system had a better docking score than the drug itself, while the result we had was for that conjugate system was less than that for the standard drug, which is Acabo. Standard Acabo is a drug that is used to or deal with diabetes. So what we can do is to export this result. So you can simply click here and then export that result. So I would love to export this under um, downloads. So I think I've done that before. So docking. Okay, so let's keep it like this, and then let's one IR3. So we can save it that way. Now, after saving it that way, what we can do is to go to Excel, and then if you want that's if you want to open that result. That's if you want to open that result. You can go to Excel and then you can navigate to that directory, open, go to we want it in, okay, sorry, so just go to open, and then you can go to browse, then let's go to downloads. Okay, now, and then all files, so we can choose to open that result. So you can see that we have the results. We have different poses. I think we should have 9 poses or 10. Okay, 9 poses. And then so this is for alkables, this is for our conjugate system, and this is for vanillin. And then you're expected to use a lot of times the most negative. Now, and then you can compare. So from this result, you can see that um, our conjugate system that contained vanillin performed better than just having the drug, but the result is less than that of the standard drug. Now, what we need to do at this point is to visualize our results, and to visualize, we'll be using Discovery Studio, but we have to convert our um, docked poses into PDB because it will be in PDB Qt. So what we need to do is to use a software called Babel. I've shown you how to do it before in other videos. So go to open Babel. So open Babel. Okay. Okay, I think I saw it. So open. Let's, okay, so this is it. So this is, click on it, this open bubble, and what we intend to do is to convert our result from, our pose is from PDBQT to PDB. So it's taking a while, but okay, so this is good. So Babel is the software that converts from PDBQT to other formats, and then you can also convert from other formats to PDBQT. So you can have the different formats, you can have SDF, SMI, and the rest. But for this work, we are going to be converting from PDBQT to PDB. So what we do is we would open, let's navigate to where we have our PDBQT files. Now I'll show you where you can find it. So what you do is simply go to local disk, go to users, yes, user. Now go to look for .mgl tools. Now go to PyRx, then go to macromolecule. Now you should be able to remember the code of the macromolecule you worked with, and you can remember, if you can remember, it's 1IR3. So click on it, and then we convert it from PDBQT to PDB. So let's start with archivables. So it's in PDBQT, and then we're expected to convert it to PDB. So to do that, we also, okay, so simply what we'll just do, I will call it archivables. Okay, archivables. So just call it archivables. Okay, let's just call it archivables, and then let's save. So it converts it from PDBQT to PDB. So that's fine. Now we are going to also carry out the same process for the conjugate system. So you can see that, and then we have to change the name so that it does not overwrite it. So for this will be Polymer Conjugate system, but remember it will be saved as PDB. So save, so convert. Okay, so this is good. And then the last one will be vanillin. So this is vanillin. Open. Okay, so we still go back there, and then I will save it as a PDB file. So vanillin, so save, and then we just simply convert. Okay, so this is fine. So we've been able to convert alcohols, vanillin, and the conjugate system. So what we need to do is to import them into um, Discovery Studio. So I'm not changing anything here. So go to insert, and we'll just navigate to that directory. Okay, so remember, don't forget it's under um, local disk, and then users, user, um, MGL tools, PyRx, macromolecules, 1IR3, and good. So what I will do, you can see it is a PDB file. So I will select everything, and then open it. Wow, so this is good. So it opened everything. Now, so let's visualize the interaction. Now, if you check this, if you click on this, you will see something. It does not click. But if I click on the second one, it works. So that's one of the challenge you find. So if you want to visualize this, so simply you can see that. Now the same way, if you try to click on this, nothing would happen, but if you click on the next, if you try to check the next one, it works. Okay, so if we want to visualize our conjugate system, so let's visualize our conjugate system. You see it's in that same region. You can see it. So let me uncheck this. Good. So you can see it. If I uncheck it, it's out. So good. So what I need to do is just click on it and then come here and then click on the find ligand and then select it. And then what you can do is to click on show 2D diagram. Wow, so this is good. Wow, wow, wow. So very good. So you can choose to make this bigger. Okay, cool. So this is good. Now, so you can see different interactions between your polymer, your drug polymer conjugate, and the different amino acids you have in that protein. So what I can do is I want this to look better. So click on this. Good. And then I want it to be stick. Oh, beautiful. So you can see that interaction. So you can see the interaction between your conjugate, your drug polymer conjugate. This is the drug, this is the polymer, your drug polymer conjugate, and the amino acid residues in that target protein. Now, so you can choose to save this. And how do you save it? Click on it and then go here and click on save as. You'll be saving it as a image file. Okay, so it's very good. It's telling me save as an image file. So we're going to save it as an image file. So okay, so we want it to be, I think this is fine. So I can select this. Okay. Okay, so this is good. Now we can also visualize the interaction between that same target protein and vanillin. And let's see, let's compare. Here we have a lot of interaction. We have van der Waals interaction, conventional hydrogen bond, pi sigma interaction, alkyl interaction, and pi alkyl interaction. Now let's see vanillin. So vanillin, this should work. So to define, so click on this, good, and then let's see. Okay, so I'm expecting this, so we should have lesser interactions. Uh, then sharp. Okay, so let's make it a stick. Now, I don't like this interaction, this unfavorable donor-donor interaction. So I would want, if you don't want to see that kind of interaction, unfavorable interactions, what you can do is, um, let's go down, see. Okay, so unfavorable donor interaction. So apply this, and then you can see that. So now, so this is the interaction between vanillin and the different amino acid residues present in that target protein. Now, compared to the number of interactions you saw when you tried to visualize a conjugate system, and you see why the conjugate system performs better. There, you would have a lot of interactions, and most likely it makes your drug more soluble and more available. So you can see that. So once you are done visualizing, then you are good to go. So let's see if we can find this. Okay, where did I save that? Oh, I can't remember. So maybe I would have to um, try to resave it. Let me try to do that and to show me where I saved it. Okay, macromolecules. Okay, so let me try to open. Okay, this is under, sorry, macromolecules. Oh, okay. So he saved it in that directory where we obtain the PDBQT file. So what you can do is you can choose to open this. Let's try to open or click on it. It's taking okay. So this is it. Now, so you can see the interaction between our drug polymer conjugate and the amino acid residues of our target protein. And if you remember, um, our drug polymer conjugate had a better docking score than the drug itself. So this is how you dock a polymer drug conjugate. Thank you for listening. If you have any challenge, please don't fail to um, put it in the comment section. I'll be there to respond to your questions. Thank you, and make sure you subscribe and like our videos. Thank you.